Hello again, students. In lesson 10.5, we're going to be learning about how to find probabilities of independent and dependent events. Now, these first couple examples we're going to go through are examples of independent events, each one of them. We'll see what happens as we figure these out. So, our first example. In a survey at Miller Park, 50 of 75 male fans and 40 of 50 female fans said that they favor the Brewers team mascot, Hank the Dog. Now, if you're a Brewers fan or if you know about this dog or if you like it, either way. If one male and one female are randomly selected, what is the probability that both favor the new mascot? So, probability of a couple of things here. Well, let's see. Event A, I'm going to say the male likes it. And event B, the female likes it. It being Hank the Dog. So if I want to figure out what these two things are, if I want the probability of A and B, and again, this key word here today is the word and. Now, in the last lesson we had the word or, and with the word or we had to add probabilities together. When I have the word and, that means I'm going to multiply a couple of different things. So these are examples of independent events. Okay? I'm asking two random people at different times, different places, and neither of their answers affects the other. So they are independent events. And if they're independent events, we can refer to that fundamental counting principle we learned about in the first lesson of the chapter, where if I have a bunch of different events that are independent of each other, I can multiply them together to find the total number of ways that those events may occur. So, probability of A and B. Well, what's the probability that the guy likes it? Well, let's say 50 out of 75. Okay? And the probability that a female fan likes the dog, well, that's 40 out of 50. So I have 50 out of 75 and 40 out of 50. Because I have the word and, I'm going to multiply these two things together. Now, rather than type that in my calculator and choose from my four multiple choice options, I'm going to simplify these fractions. 50 out of 75 reduces to 2/3, and 40 out of 50 would reduce to 4/5. I'm going to multiply 2/3 times 4/5. 2 times 4 is 8. 3 times 5 is 15. 8/15 would be the probability of both of these fans liking the new mascot, Hank the Dog. So 8 out of 15. In our next example, a survey found that 46% of parents surveyed said they read to their children at least once a week. If 3 parents are selected at random, what is the probability that all 3 will say that they read to their children at least once a week? Now, once again, if we're going to do a random survey here, asking one parent, do you read to your kids? And then we ask a different parent, do you read to your kids? And then we ask a different parent, do you read to your kids? None of those events affect each other. Parent A, parent B, parent C, they're all different events, they're all different questions being asked, different people, so their answers don't affect each other. That being the case, this is once again an example of an independent event. And if it's an independent event, I'm going to go ahead and multiply the different probabilities together. So the probability of the first parent saying, yes, I read, well, that's 46%, or 0.46. There's parent A. Parent B, same percentage according to the survey, so we're going to take 0.46 again. Parent C, same percentage once again, so another 0.46. And because, again, these are independent events, and I want to find the probability of all 3 saying, yes, I read to my kids once a week, we're going to multiply those together. So 0.46 times 0.46 times 0.46 is going to be about 0.097. Okay. If you want to think about that as a percentage, it's about 9.7% probability that all 3 are going to say, yes, I read to my children at least once a week. Our last example for this first portion is a place where we're going to have independent events at work. So during each of the 5 days of a special week, an employee is randomly given one of 10 prizes. All prizes are available each day, and one of the prizes is a $500 gift certificate. What is the probability that an employee receives the $500 prize at least once? Now it says receiving that prize at least once. That makes me think about something. So if I were to think about the fact that I've got 5 different days of the week with which I'm working, what's the probability that the employee gets that gift card on the first day? Well, he's got a 1 out of 10, right? And then on Tuesday, because you could get, each prize is available every day, he has another 1 in 10 chance of getting it on Tuesday, 1 in 10 chance on Wednesday, 1 in 10 on Thursday, and 1 in 10 on Friday. Now, the key here is that the problem said, what's the probability he gets it at least once? Now, if it was just once, we could probably figure out, it'd be just one time, and then we'd be done with it. But it says at least once. So that means he could win the prize 1 time, or he could win the prize twice, or he could win the prize 3 times, or he could win the prize 4 times, or 5 times. You get the idea. When we use the word or, it means we're going to have to add a whole bunch of different probabilities together. So an easier way to work with this would be to use the complement. We learned about the complement in the last lesson. In this case, the complement would be, he doesn't get the prize at all. So if the probability of A, event A, we have the probability of winning the prize at least once. Again, we said there's a bunch of different options, right? The complement to that, A bar, would be the probability of, what's the opposite of getting at least once? Never winning the prize. Now in this case, the probability of never winning the prize is a little bit easy to figure out, because what's the probability that he doesn't get the prize? Well, it'd be the complement to this. It'd be 1 minus 1/10, or it would be 9/10. And then Tuesday, again, 9/10. And then Wednesday, again, 9/10. And then Thursday, 9/10. And on Friday, 9/10. So we're saying we'd rather figure out him not winning the prize at all. Or her, I should say. So, the probability of event A happening, which is really what we want in this problem, is equal to 1 minus the probability of A bar, the complement, which in this case is much easier to figure. Because I know the probability of that happening is the same each day. It's 9/10 each day. Or I could change it to 0.9. But now, since it's each day, each of these are independent of each other, I'm going to multiply all of those together. 5 days worth of 9/10 probability of not winning the prize means we're going to take 0.9 and raise it to the 5th power. 0.9 times 0.9 times 0.9 times 0.9 times 0.9. So I take 1 minus whatever that number is, and that's going to give me the probability of winning the prize at least once. So, typing that into the calculator, saving a little bit of time. Our final probability is about 0.41. So he's got about, you want to think of this as a percentage, about 41% probability that he's going to win that $500 gift certificate at least once, which is a pretty good deal in my opinion.